possibility of applying graph theory in vast area, and another important like in lightweight security technologies. So with the existence of all those things and the proper development in all those areas, actually nowadays we can think about the IoT or whatever cyber physical systems what we are talking about. So theoretically, as an academician, if we see from the academic point of view, if we see, if you want to work in IoT, so better to identify in which area you want to work. And those areas are already, either someone of you are very well and well equipped with this embed system design. So you can focus on that part. Some of you, if you are very inclined to this networking part, so there are huge problems, huge enormous scope of work in the networking part application to IoT. So if you want to do some communication part, obviously 5G, the application of whole 5G is for this one, 5G beyond. If you want to do more theoretical part on this, or if everything everywhere, ultimately the concept of IoT and cyber physical systems, it would be a distributed kind of thing. So somehow you have to take the inferences at any point, and that inferences means either you have to do some detection algorithm or you have to run some estimation algorithm. So theoretically, if you want on this IoT and cyber physical area, so one great theoretical aspect is this distributed detection and estimation things. Okay, and another way of doing that like machine learning. So you have huge data, you have huge connected sensors. Okay, and you can get huge data, so you have the big data analysis you can do. Parallelly, you can apply your machine learning algorithms to learn the system to take the futuristic some things. So in there also some if someone want to do something, so theoretically they work in the area of the statistical learning, or in practice they want to do, so they can use so many machine learning tools are available, so they can apply those tools for the existing data, can take the inferences and can do the things. The security part, obviously in case of IoT, as in case of IoT or cyber physical system, our main target is not always the big computers which have huge processing power and memory. It may be anything like very lightweight embedded system, like suppose your Raspberry Pi device, or your simply one small battery powered some simple SoCs, or some lightweight mobile. Okay, or some only sensors with a communication feasibility. So in those cases, the main idea of this security, so whatever the work in the IoT domain for the security part, you have to always think about the lightweight security things. Lightweight, lightweight solutions. So lightweight solutions in terms of, obviously the processing power should not be that high. Similarly, simultaneously, it has to support all the modern. It has to compare with all the modern threats. So, some kind of public key cryptography systems with lightweight keys, and those things should be applicable. So these are the things, the subject wise. So IoT actually, and obviously the optimization. So you are taking decisions from several sensors. Ultimately, you have to do some distributed fusions, or you have to take a you have to solve a optimization problem. So either any of those inference problem or optimization problem you have to solve to get these value added services by engaging all the devices connected in your network. So ultimately optimization in theoretical perspective, if anyone to work, so they can work on this optimization technique also. So one is inference things where actually we can theoretically we can stress on this detection and estimation things. Another is optimization type of problems where we can exploit different optimization things. And in terms of design part, you can think about this embed system, okay, or some machine learning algorithms to apply the AI or whatever we want to say nowadays. And another aspect of great aspect is the security part, where you always have to think about the lightweight solutions, as all the devices in the most of the devices, you can't say all, but most of the devices in uh, IoT environment are not equipped with high-end processor or memory. Okay, so that those things are the constraint. And everything, this all these IT concepts and this cyber physical system concept is nowadays realizable practically. The main reason is that we have now communication, very intelligent communication techniques like this 5G, where we can share the spectrum, where we can jump from one spectrum to another spectrum, where we can use seamless connectivity between different standards. Okay, and other part is that, so this communication and this development of this embedded system. So today, so we'll stress on these two part and the inference algorithms. So if this advent of the embedded system, so we have started with the transistor, now we can go for the SoCs. So even IoT will not be feasible if the concept of SoC was not there. So system on chip, concept of system on chip was another key enabling term for today's concept of IoT and the cyber physical system. So these things you can thought about. Okay. So the main points, so three main points we can tell. So all these topics what we have discussed, all are interested, and understanding the big picture helps for following each individual topic, obviously. And it gives you a better idea about the scope of the subject as I discussed now. But parallelly, it let us better calibrate the course based on your interest and background, as I told. So it is not necessarily all who will be working on a communication domain, he will be working in the embed system domain, or he'll be working in the security domain, or he'll be working in the networking domain. So based on your own interest and your own background, you have to stress on that part of this IoT to do your research and to understand the inside of things better way, and to contribute in this field from each of the individual. So you can you will not be able to do the everything, because it is a vast, it is actually multidisciplinary subject. This IoT as well as this cyber physical system, these are the multidisciplinary subjects. So you have to identify your domain and obviously your interest, so to contribute for this in this domain. Okay. So in this ITUR 66 release 66, so some resolution has been taken about this IoT. So IoT, they are telling that this IoT is a concept encompassing various platforms, applications, and technologies. So you can see, you have see already in this communication architecture part. So in general architecture, where we are mainly stressing on this communication part, so there may be wireless, Wi-Fi, short range, where mobile, cellular communication, satellite communication, okay, cable, fiber, everything. So different platforms are there. So same way, you can think in terms of embedded system. There are several platforms should be there to conceptualize this IoT. Like you need the DSP, you need the FPG, you need the concept of SoC. So everything, different platforms, applications and technologies. And obviously there are different standards, seamless connectivity of different standards like GSM, GPS, 4G, okay, Wi-Fi, everything. So, um, so different applications, platforms, and technologies all are required, and a global infrastructure for the information society, enabling these advanced services by interconnecting the physical and virtual things. Okay, so mainly the IoT, still IoT actually focusing on these things like physical things and virtual things, where obviously these things are not the living things. When we talk about the cyber physical system, more generally cyber physical human system, so they are the human or the living beings will be also be treated as things. Okay, so interconnecting physical and virtual things based on existing and evolving interoperable information and communication technology. So at these international telecommunication units, so they mainly actually focusing on this communication and information part. Okay, not the processing or embedded part much, because that is not their domain. So some why IT is required to think. So again, from the with the language of ITU, so to design, to make buildings and deploying applications for easier, faster, and secure and more accessible to everyone. So this term is one key important for what the example we have given. So if you can monitor your elderly parents who are staying at home, if you can monitor their health conditions through your smartphone, where when you are in the office or far abroad, so there is nothing good than that, right? So if this type of accessibility to you, so you can do a lot. You can concentrate on your job, parallel you can take care about your family, okay, wherever you are in the world, even, right? Same way like smart home, so you can monitor the whole systems of your home. So accessibility will be uh, more everyone, but parallel it should be secure, right? It should not go to any other one. So that level of security is also required, so that nobody can no eavesdrop or can be entered there. And it allows to create the low power. So this is another keyword. So IoT or cyber, whatever, it should be designed such a way the issue of the power uh, should be there. So admit that means it should be always somehow the protocols, the technologies should be facilitate the low power things. Okay, and parallelly it should be wide area based. So not only in a small area, it would be, if it is a small area concentrated, that also can be called as a IoT, but in general it should allow wide area. So wide area sensors and actuators network systems for machine type communications. Okay, so so vehicle to vehicle, machine to machine communication. So in there are specific uh, protocols are there in the machine to machine communications, and the smart cities and ubiquitous sensors networks. So this machine to machine communication, somehow you can think about like the wireless sensor network somehow, but obviously with more constraints. like, so there would be very low latency communication, there should be very low latency communication in case of specifically for this machine to machine communications, small packet communication. So this type of more constraints are there, but in general you can think those are actually somehow wireless sensor network. So the concept of wireless sensor network, so with the advent of the wireless sensor network, again this networking part of the wireless sensor network will be used. The networking part of the IoT actually nothing but quite similar to this wireless sensor networks. Okay, yeah. So if we see the use cases of IoT, so it may be in rural case, it may be in urban areas, dense urban, and spectrum wise, it may be use licensed band or unlicensed band. So obviously, if it is unlicensed, it may be used for commercial service, where it may be public or private, and sorry. Uh, so and type of networks, obviously it may be from land to WAN everywhere, and same way like private mobile to telemetry to machine, everywhere satellite, every type of network should be involved there. Okay, so this is a one kind of summary chart, you can say, whatever we have seen. Again, we're coming to this connectivity options. We want to share few things in this connectivity options, like the as I told here. So there may be so licensed band as well as unlicensed band. Okay, this licensed band and unlicensed band. So we have seen most of the, we used to do so many IoT related solutions in our projects, in our institute. We all used to do for with the students projects, we used to do, we all. So in there we mainly we have used the unlicensed band. Okay, so the devices, the embedded systems what we use, they are capable to work in the unlicensed band, because there is no much constraints and we can use freely. But the one major issue will be there in the unlicensed band, the interference. Okay, so as we know, 2.4 gigahertz or 5.5 gigahertz range, the sub 6 gigahertz range, those unlicensed band we can use. But the major issue will be there in broad sense. If you see, suppose you want to make a industry automated, so you need huge number of sensors, huge number of actuators, and so many other devices. So in that case, sometimes it may happen in one location, the whole unlicensed band may be not enough. Okay, so in that cases, some part of the IoT can be also done through the licensed band. Even not only that, even some works actually used to perform, you have to perform in the licensed band only, because some critical services are there where you can't use the unlicensed band even. So, uh, so technically this machine to machine, this node B IoT, this LoRa, they are actually some uh, uh, already existing cellular and non-cellular um, uh, systems available. Okay, and this is already reported by, studied by ITU under this World Radio Congress in 2019. Okay, already several these standards already existing, some commercial, some in licensed band, some in cellular band, some in non-cellular band. Okay, and they all exist. on their own way they are progressing in different regions, and the spectrum part of this IoT is the the what we actually need the spectrum for this IoT. So to determine by each application throughput. So how much spectrum will be required? So it will depend on this throughput. So and another is the latency. So I think you know the basic definition of this throughput. Throughput is the output per unit time, right? And latency is the initial delay to get the first output from the first input, right? So depending on this throughput and latency, the spectrum will be defined. Like for a given spectral efficiency, uh, if we need the low latency, means it should latency delay should be less. Okay, if we want that, so obviously we have to go for the higher bandwidth, right? So same way, while different IT applications might not need high speed connections, okay, have very stringent latency requirements. Some latency stringent latency requirements. For example, you can say some remote surgery you are doing. Okay, so in that case, latency is one of the important part. Okay, so in those cases, uh, you need more bandwidth, right? So just think from our remote, you are doing operate, you are monitoring one operation from doing remote surgery from Vellore to or Apollo Chennai to your village. Some doctor is doing so. You have to give that bandwidth throughout this connection. Okay, so that infrastructure should be there. So you can't rely always on the cellular part there. Okay, some in between you can rely, or some part you have to rely on the satellite part. Some part you have to rely on that when once it will be in the inside the dense urban area, you have to somehow rely with this mesh network kind of thing. And once it will be in the remote or rural area, you somehow you can use the um, seamless satellite parts a little bit, and some of the more um, communications. So this is a combination of all those things. And in what frequency band it will be used, so it will depend on the application to application also. Now, same thing actually, this so spectrum for this machine to machine IoT applications, as we told, these are unlicensed and licensed, both are there. So this licensed may be either mobile operator network or some dedicated network will be used, like LT vehicle to X trials. This one they are using this some mobile licensed spectrum, but it is a dedicated network. Okay, nobody, it is not used in any other mobile operation. You can also use the conventional uh, LT network also for the mobile operator network, where it is same infrastructure is available and you can use it. And unlicensed is always there, and but the limitations and the traffic is increasing, so you have to take care about that part also. So if you see there this graph, so the summary of this IoT graph. So as the uh, license, if you as you go to the um, license exempt spectrum, so obviously. all the recent the Sigfox, LoRa is used in this Amsterdam. They have used there. So uh, it is some French collaboration is there. So they all these things are coming in mostly in this license exempted band. Still, in terms of license band, obviously the development of this IoT is less because of the main reason is that uh, why we'll pay. If without paying anyone we can develop our design, that is obviously good, right? So we also used to target the all unlicensed band uh, for our own project or development, right? So the same way it has been also evolved in this only unlicensed spectrum. But obviously, and most of the development has done still now in this local area, mainly in this local area. Okay, so local area, mainly whatever the applications people have developed, commercially available things. Many of them are mainly targeted the local area, but other wide area network also is coming up. But still, the we need a more contribution in this field, and obviously somehow this as the license spectrum are already occupied by some users. So if with the advent of this cognitive radio kind of concept, okay, so partial use of those license spectrum can be thought, and that way people are thinking nowadays. So it should not be completely licensed spectrum because the cost will be high, running cost will be high, and it will not be a cost effective solutions for in general. So somehow if partially uh, use can be done with the concept of this cognitive radio thing by sharing the spectrum when it is not used by the licensed user. So somehow in that way, some low cost solutions which are exploiting the license spectrum can be thought. Okay. So the now just one simple difference between this cyber physical system, as I said, to discuss just one point. The scope of IoT actually is up to this communication part, okay, communication and the decision part. But the interaction with the physical things, interaction with the physical things, okay. So this part, if we consider, so that is actually the cyber physical system, you can say. Though this definition is not completely, I can say, foolproof, but somehow we can define, somehow we can differentiate the cyber physical system and IoT in that way. So ultimately, whatever the communication you are doing, this networking, the decision making means all the inferencing and the data fusion, okay, all the computations, you can say all these are the part of your IoT research scope. And when actually you are linking that part with the physical system, so that way you can say that is the whole things actually the this cyber physical system, you can say. Okay. And somehow this linking part also involves the economy, also involves the all these things. So I am not going much inside into that part. So there is a nice concept map of this cyber physical system. You can get it from the cyberphysicalsystem.org. So it actually telling how the cyber physical system are related to the different topics of society, right? It is related with the security part. It is related application wise. It has different aspects from the requirement part. From requirement side, it has different aspects. From the feedback system point of view, it has different aspects. So that way you can say somehow it is a greater say IoT. You can say somehow a subset of this cyber physical systems. Okay. So three basic ways to achieve all these. Okay. So again for designing this IoT things, we have to think the three basic ways of designing approach. Okay. So these three basic ways are actually we have to use. One is the analysis part, how we are analyzing. So do, we have to analyze it for say performance bounds. Okay, so that means for the worst case performance bound we have to analyze it. So like analysis typically suppose relies on the exact information on all the components of in the system. The worst case performance bounds can be pretty bad, but that for example, in terms of suppose embedded system point of view, if we think this one, so the cache memory is typical one example of this one. So we cannot compute the exact cache state. Then using cache actually leads to a decrease in performance in the worst case, right? So if we are unable to actually compute the how much it is using there, and it will be also the increase the cost. And the next important thing is the based on this analysis you have to modify your the system. Suppose you have seen so only a single FPG is not workable. In better if you can use a combination of soft IP core with a FPGA, that is better. Okay, that means suppose if you use a ARM processor with a FPGA processor, that will be better because you need sometimes very fast processing and sometimes you need very complex processing where which actually not always possible to code in the FPGA. So that way, that type of combination, so this type of modification you have to do by analyzing the your requirements and the system. So by with proper analysis, you have to modify the architecture of your system, and this analysis will also change from requirement to requirement. If your requirement is changing, obviously it will also change, and based on that change, your modification will also be some change. And then, like the complexity of changing different portions of the architecture is not the same, obviously. So if someone is telling you you have to design your core again, so it is very tough, very expensive also, right? So if interconnects new architecture, okay, suppose somehow if someone is telling you have to make the all the things wirelessly, suppose your application is such a way that your interconnection should be wireless, there should not be any wire connection, suppose it is not feasible even. So that still can be done, but uh, core redesign is expensive. So and the so leave the core as it is and adapt the rest of the. So the somehow the main idea for this modification part after analysis, generally people use the keeping the uh, core as it is and adapt rest to support more predictable performance. And that is the reason if you see nowadays from system on chip point of view, uh, they are giving any part. Suppose a PGA in Xilinx FPGA you will find one IO processor. Okay, IO processor. So IO core. So this core they are giving the core as a soft IP core. Okay, so you can dump it on your hardware FPGA and you can run it as when it is required. So because you need not to change the core every time. So they are giving the net list, get net list. So as a hard IP core or in terms of some soft IP core like the Verilog code itself, they are giving whenever you have required that code, you can dump it and you can reuse it. So reusability of the core is one of the major concern of this nowadays, major concern from the embed system point of view again for this IoT design. We'll come to that embedded system point of view. If you still now whatever we are mainly discussing, we have discussed mainly from that um, uh, communication and networking point of view. So gradually now let us go to the embed system point of view. So and redesign as you told. So in the embed system, as we know nowadays, this all those high-end modern high-end cars. Okay, so hundreds of processors are there. So how these processors are integrated with each other, how these sensors, number of sensors are there, or in a medical system, enormous number of processors as well as the um, uh, their interconnectivity is required, right? So these all are the examples of complex embed system, and this computing system embed system is somehow facilitating the computing system in more lighter way, not only depending on the general purpose processor. A specific computation can be done on a specific small embed system. So that is the basic idea of this embed system, and that it has been developed so a small and this with the advent of this embed system only in today's as I told today's IoT is feasible. And if you see the market uh, of the embed system from initially the PC market was quite high, but once the concept of an embedded system realized, nowadays this PC market, this personal computer CPU, okay, this market is now uh, is shifted to this embedded system part. So it is now quite this 2003 report I am showing, but nowadays it is quite manifold. Okay, manifold of the around 100 folds of this PC market, because nowadays your pad from where I am writing you, this pad is now you can say a small PC, but actually your smartphone, all those things actually are the examples of your embed system. So how many PCs you have in your home, and how many smartphone you have in your at your home. If you have 5 members, you have at least five smartphones at least. So and you have suppose one laptop or one desktop. So at least double or triple. Okay. So same way, the market of the embedded system is increasing, okay, very rapidly, and that is actually one way. As again, I told very beginning. So market of the embedded system, advent of the embedded system, more complex complex things can now be possible with small embedded systems, because the concept of SOCs are coming up, already came even, and using all the embedded system processors, are previous microcontrollers are replaced now with those SOCs. And parallelly, the advent of communication systems, specifically 4G and this low latency, high throughput, high spectrally efficient communication standards, availability of those, implementation of those standards like 4G and 5G and beyond. Okay, so if based on these two things, means one is this communication part, another is the advent in the embedded system part, the whole concept of IoT is possible. So in terms of embedded system, the main key driving force for this IoT is the SoC, so system on chip. If you see, so the Moore's law, so as we know, every 2 years, so number of transistors will be doubled. Okay, same way, the memory development also improved, and even it has improved more than the microprocessor. Okay, so this memory development somehow overshoots the this Moore's law. Okay, so we have now huge memory available with very small, cheap price, very small size, and parallelly, the concept of energy also came. So we can do so many things. So these main challenges were there in the wireless sensor network. So energy dissipation and the size. So the size actually somehow can, size, because if you want to put to do a lot of work, if you want to put a CPU itself, so it is the size matters. But once the concept of system or chip came, or SoC came, so somehow we can overcome those things. Now what is happening in the microelectronic field, SoC paradigm? So previously we had, so previously we have only few gates. Okay, now then then we have improved to, some more gates with schematic and synthesis. Now again we have improved to more gates with emulation, simulation, and synthesis from as our technology is also improved. So our technology is also improving. Now in that way, now we are becoming with the same wafer size, with the same wafer size, initially where we used to put only few gates. Now we can put few different processing units. Okay, so the everything it was possible because the huge advent in the area of microelectronics. Okay, the concept of so it came now new design paradigm. So previously you used to put few gates on the wafer. Now you are putting few different processor on a wafer. So now you can make different processor. Okay, different processor in a single wafer. So and the concept of SOC actually came to in real world. Okay, and we have good level of interconnectivity among all those things. So you are able to realize so many works in a small, very small place. So the power of computation increased, and it actually the concept of this SoC and realization of the SoC actually remove the constraints of the size. Okay, so with this one, we are able to uh, uh, see. So and there are mainly three forms of SoC design. You can say one is this ASIC vendor design, another is this integrated design, and another is desktop design. So in ASIC vendor design, it actually refers to the design in which all the components in the chip are designed as well as fabricated by the ASIC vendor itself. So like suppose you want to make your own chip. So people, the vendor itself, they are designing and fabricating. In case of integrated design, it refers to the design by an ASIC vendor in which all components are not designed by the vendor. It implies the use of cores, like suppose, for example, like TMC, Taiwan manufacturing company. So they used to take the cores from different companies, they make combine it, and they are manufacturing actually. Okay, uh, but it is not necessarily all the designs will be all the designs are their own. Okay, they can take it from us also as a code. And another type of SC design companies are like who are actually generating the soft codes, you can say. So either in using the EDA tools, they are simply designing the soft codes. So they don't have, you can say, they are the fabless IC companies. So now some vendors, they are combining so many uh, good parts from different these fabless companies, and they are making a single SoCs. Okay, it's not necessarily all the cores. So these are the cores. You can say, see, this is one core, this is another core, this is another core or processor. You can say, okay. So all the cores are not may not be made from a single vendor. So it can be some who is actually manufacturing. He can combine it from different vendors and can get it from different vendors and can combine it. So this type of design flow is there. Yes, yes. So all those flexibility actually, again I'm telling. So availability of all those flexibility uh, ultimately helping uh, to materialize the concept of this RT. And uh, however, one basic challenges of SOCs was like average turnaround time. So how much from the concept to the ultimate net list. Okay, so it is also very uh, high, but if one has to do it, so one vendor has to do all the course, it will be more. But nowadays it is available with so many this desktop manufacturers, like desktop design units. So who will be making ultimately, who will be manufacturing ultimately the physical chip, so they will simply buy it from different vendors. So that way the average turnaround time is also reduced. And another thing of for an ASIC, the following factors influence this, like number of clock domains. So how many, and the average turnaround time also depends on how, if in which frequency the design should work. So based on that one, so if it is very high frequency, so obviously the power will be one issue during design. So if number of clock domains, if it is working in multiple clock domains. So congestion is one great issue. Okay, and if the big design or small design, so density of the mm, design and number of blocks, half blocks, everything depends on this turnaround time. But anyhow, this turnaround time can be averaged out nowadays because the availability of different uh, desktop these design houses. Okay, so we can combine from different things. And another issue of or challenge you can say in this SoC design, as we told, the this RAM technology, memory technology, and the basic processor technologies are not same. Okay, but once they are combined in one chip, so this is the processor part. So suppose this is the processor part, and this is the memory part. So once you will be combining inside, previously it was off chip bus. Okay, so but once you are combining both in a within a chip, within a system or on chip, so you need a on chip high communication bus. Okay, so leverage internal bandwidth versus external bandwidth is another challenge for this one. This is the design. So, but somehow we are also there are so many houses they are working on this, and that we can see that SoC and ASIC are not same. Even not only that, in this case, in if we are talking, this is SoC. This is one SoC. So this may be one FPGA. Suppose this may be one ASIC chip. So this may be one DSP. Okay. So that means SOC SOC does not mean all are ASICs. So one of the core of this SOC may be ASIC. Other may be some FPGA, other may be some DSP, other may be some ARM processor. So that is another level of advantage of this SOC is giving to implement the IoT. So there are so many things in IoT. Some part can be done to suppose some very fast processing is required, and we can easily implement on FPGA, so that can be done. But some suppose say, some um, changing someone suppose some image processing algorithm, which is actually change, which may be changed based on the requirement or quality of service. So that can be easily implemented on in one ARM or DSP processor rather than an FPGA or ASIC chip. So this type of flexibility is required to implement or this, that means the IoT in real life, and that actually SoC is giving. So SoC and ASIC, there is a huge difference. SoC is not the ASIC. So ASIC may be one part of the SoC, but ultimately whole the SoC will be realized through the ASIC flow only. Okay. So some soft core will be there, some hard core will be there, and those cores can be used from different vendors. Okay. So that we want to say. Okay, same thing like for higher performance, much higher levels of integration, and for commercial blocks, we use those so different IP cores, platforms, and reusability. So these things are big. And if we see the technology versus productivity versus complexity, so if we plot in three different axes, so SOC actually ultimately the technology will be more, will be more, this technology means get to source distance, right? Get to source distance in a transistor. So this technology means, technology improving means it will be reduced. So some, that way it will be reduced. Okay. And design complexity obviously will be high and high. It will be always higher, and productivity should be more. So somehow SOC will always should go in this situation where more technological advancement should be there. Okay, more to cope up with high design complexity with higher productivity. So that is the ultimate goal for SOC, and obviously this will help to realize the more applications, more real practical implementation of the IoT systems. And in the similar, just this is a course, as I told, there are different type of course. It may be soft core, it may be hard core, it may be some firmware core. Okay, and it depends on their usability, portability, flexibility, and obviously another axis you can say the performance and time to market. Every those things are used. Okay, so based on those things. So these are some the basic idea of these two major blocks of the IoT, like this combination things and the embed things we are highlighting here. So another thing is security is there, which will be also covered in somewhere. And in this, except this one, I want to stress on the two major things. One is the this inference part. So the inference part, uh, 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 this inferencing part is actually somehow theoretically, as we discussed, it is related to this decision theory or the estimation theory. So I want to see this IoT, one major building block, um, as this decision tree as a major building block for these IoT things, because so inferencing or optimization problems are the ultimately two types of problems are handled in this IoT systems. So we'll mainly focus on this decision theory and estimation theory a little bit from the theoretical point of view. So, the decision theory. So let us see the basic components of a decision theory. So if you see in the decision theory, the three basic components are one is the source of information, and there is one probabilistic transition mechanism, means the decision or estimation of a parameter. All these are some inference problem. Either you are inferencing about a source or about a parameter of interest. So here the main component, one is source, one is some probabilistic transition mechanism, and another is some observation space. So for example, you have a, suppose, defense system. Okay, so one enemy aircraft is coming or not coming, something is happening, and you have your own radar system. So you are observing from this observation space, and based on your observation of that event, okay, so whether that event, when enemy aircraft was there, whether yes or whether no. Okay, something is happening, either it is coming or not, and you are observing through some noisy environment, suppose. So you don't have the exact idea, or somehow you can make it as a think it as a probabilistic transition mechanism. So, and you are observing by sitting on your observation space. So based on your decision, you are applying some decision rule on your observation. Okay, yes or no, and that way you are taking the decision to fire your defense system, your missile system for this enemy aircraft. So that is the happening. So if we can define this uh, two hypotheses. So you can say there are two hypotheses. This is a binary hypothesis system. So one is H1 and another is H0. So H1 we can say it is, you can think about H1 is the enemy aircraft was there, and H0 no aircraft was there, and you have observed the things over a noisy environment. So suppose you have two hypotheses, so null and alternate hypothesis. So H1 is the alternate hypothesis and H0 is the null hypothesis. So you have to test which hypothesis was true. Basically, ultimately, you have to design the rule to test. So the ultimate aim of the decision theory is you have to design a rule to test which hypothesis was true. Okay. So suppose why is the transmitted things actually some transmitted signal, and X is the received signal. So in null hypothesis, you have received only noise. Okay. So N is the noise, you have received only noise. In null hypothesis, you have received only noise. Fine. And in the alternate hypothesis, you have received some signal over noise. So now you have two hypothesis, H1, which is x equal to y plus n, y and n. Another is H0, which is x plus n. And it is a simple binary hypothesis testing. You are defining that way. Now, decision rule is the finding of a rule or threshold, you can say, if this is the threshold and if your x, so this is your threshold, if somehow x is above this threshold, you will say hypothesis H1 is true. If x is below the threshold, you will say hypothesis H0 is the true. So that which one is the case you have to find, and the decision rule actually ultimately will find that threshold. So to find the threshold for what? threshold for some test statistics. So this threshold for some test statistics. Okay. So this test statistic you can say either energy of the signal, energy or amplitude of the signal means x of received signal. Okay. So either energy, amplitude or sign of the received signal, those are used for the test statistics. Now see the simplest binary hypothesis testing we have. Hypothesis testing, basically the binary hypothesis testing we have considered. Now see how many cases actually may be there. Suppose here you are observing, so you can observe H1 and actually H1 was sent. That may be case. But you have observed here H1, but actually, so H1 was there, you have observed H1. H0 was there, you have observed H1. You can observe H0 also. Suppose H1 was there, so you have observed H0. Or the actual H0 was there, you have observed that H0. So these four possible cases may be there, right? So now see how many different events can be observed. So one thing can be happen, given H1, okay, you have observed, given H1 means H1, this X was, you can say, this is the, according to your this equation, Y was sent and X was received. So here you are receiving Y. So, so this is Y, you have sent X. So different things, what the different things can happen? One thing may happen, okay, X was Y was there and you have received X. That is the ultimate thing. So it may happen H1 was there, you have also observed H1. So this event is called the probability of detection. So these are basically CDF. So the probability distribution, probability cumulative distribution function, this P. So the probability of detection, we call this one probability of correct detection or probability of detection. So H1 was there, something was there, and you have observed it was there. So this may be one case. This is called actually probability of correct detection or detection. Now another case may be there. Y was H0 means nothing was there, only noise was there. But somehow you got your somehow you calculated X such a way that it crossed the threshold. You are detecting it as a H1. Okay, so that means it can be called as nothing was there, but you have detected something was there. So probability of H1 given H0. Given H0 means Y was H0 and you are finding the probability of X. So this is also a cumulative distribution function and it is in term it can be coined as the probability of false alarm. Means nothing was there. So nothing was there. You are simply screaming out. Okay, aircraft came, but this is actually somehow false alarm you are generating. So that's why it is called the probability of false alarm. And another scenario may happen. There was some aircraft H1 means why was something was there. Okay, but you have detected somehow your received signal X is so low. I mean, suppose energy, for example, or amplitude, for example. It was so low somehow because you are observing through a probabilistic mechanism or noisy environment. So you are telling that okay, you have detected that that is 80, nothing was there. So actually you have missed that aircraft to fire. So that's why it is called a probability of miss. And another is probability of nothing was there, you have also told nothing. So nothing has been detected, nothing. So no meaning you can say that from the decision point of view. So these three type of definitions are important to understand this decision theory. So one thing may be probability of correct detection, probability of false alarm, probability of misdetection, and the error in the testing. If you see among these three things, so the second and third actually some kind of error. Something was there and you have missed that one. So that is one error. Another thing, nothing was there, but you are telling something was there. That is also another error. So these two type of error is called type 1 error and type 2 error. So probability of false alarm is called the type 1 error and probability of miss is called the type 2 error. And in some case, in most of the cases, this type 1 error is somehow more costly. Okay, like for example, if nothing was there and you have fired your missile, no aircraft was there, you have fired your missile, means the cost, you have lost a huge cost. So that's why it is costly. And something was there, means aircraft was there, you forget to fire, that is type 2 error. That is also costly, but at least not costly like, but you have not lost your missile cost, right? So, so that way it is, it can be assumed as a less costly error than the type 1 error. So somehow type 1 error are naturally more costly. So these few definitions are required to understand the decision theory. One is binary hypothesis testing problem, then the different scenarios, events of this binary hypothesis testing problem, and the definitions of this probability of correct detection, probability of false alarm, and probability of miss. Okay. Now, if we plot the these functions, probability of um, alternate hypothesis, and so let us see this left side top figure. So I have plotted the probability of x under h0 with this curve. Suppose this is a Gaussian curve. For example, let us take this example. So n is suppose 0 mean some variance, and y has some suppose, so that way y has some suppose 1 or something. So in that way I can say probability of x under h0, it is actually a normal distribution given sigma square, and probability of x under h1, it is also normal distribution with some unit mean and variance sigma square. That actually we are plotting here. So suppose this is the normal distribution with zero mean some sigma square, and this one is the normal distribution with unit mean some sigma square. So some variance. So if we see these are the two plots of these two distributions and the null hypothesis and alternate hypothesis. So the area under the curve of H1, this red shaded area what we I am doing, this area actually is called the probability of detection. Means this is the threshold we are considering, threshold. So from this threshold, if anything under the curve H1 to the right side, we say this is the area of the probability of detection. Okay, and region R you can say. So in this here region is Z1 and Z0 you can say. So this region R and this is region R0. So so this is called the probability of detection. Now another uh, graphical representation of the probability of false alarm would be the area under the curve of H0. Area under the curve H0 from the threshold. Okay, so this will be actually the probability of false alarm. Means null hypothesis, area under the from the threshold to the area under the curve to the right side, area under the null hypothesis curve, we can say is the false alarm. So now, what should be the aim of any decision rule? What should be the aim of any decision rule? So if we can separate out these two distributions, suppose one is this one and another is this one. This is under H1 or H0. This is under H1. If we separate out these two as much as possible, so our decision will be better, right? Our decision will be better. So if I can put my threshold here and I can pull these two distributions into opposite directions, that will be better. Okay, that may be the case. Another case may be, so if you see this second graph in the left side, so this part is the probability of false alarm. This blue part here is probability of false alarm, and this red part here they have done it red part, but this whole area, this green, so this whole area actually, this is actually probability of PD. Okay, probability of correct direction. So what may be the case? Either you can pull these two curves in the two opposite directions, or you fix one, and pull the other curve to the another one direction. Means either you can fix this null hypothesis curve and can pull this alternate hypothesis to the right. That way also the separation between the two curves will be improved, or you can do both the curves into the opposite directions. You can pull both the curves in opposite directions. Both the way the difference or separation between these two curves will be more. Our main aim is to make the difference between these two curves more, so that we can detect them separately. Fine. So that is the main aim. So our main aim is to detect these two curves separately. Now obviously suppose two people are sitting very closely and with same height, same thing. If we are observing from distance, so it is very tough. So if we can uh, tell them to sit by keep more space between them, it is easier to us, easier for us, it will be easier for us to detect them separately, right? The same thing actually we are doing. Either we can tell both the persons to go to sit far apart, or keeping one person in one place, another person is shifted. That may be the case. So same way actually these two decision rules also used here. Either you are in one method, you are pulling the two distributions into opposite directions, and in the another method you are keeping one, like keeping this one distribution in one place and pulling the alternate distribution into the right. Okay, so the first method, so there are two methods. One is called actually Bayesian method, okay, and another is called actually the Neyman Pearson method. So these are the two, whatever the decision rules are used throughout the literature, means throughout any decision problem, they are either this Neyman Pearson method or the Bayesian method. So what actually we are doing in Bayesian method, in Neyman Pearson method, see the curve. So in the Neyman Pearson method, NP method, okay, the NP method, in the NP method, what we are doing, in the NP method, Neyman Pearson method, we are fixing PF. So it is false alarm, we are keeping to a constant value, suppose some alpha. Okay, that means we are fixing this curve, this null hypothesis curve. So fixing H0 curve, trying to maximize probability of detection, means pulling H1 curve to right. To right side. Yes, that means what we are doing, by we are fixing this PF, we are fixing this PF, okay, this PF we are fixing, PF portion we are fixing, that means we are fixing the fixing the H0 curve. Now we are pulling this curve towards the, so what actually happening, so previously the red shaded area was the PD. Now PD has improved. Okay, here the only red shaded area. Okay, let me do the red only, correct. So now what is happening? This red shaded area is increasing, right? Previously this was the only, sorry, this was the only red shaded area. Now you will see the red shaded area has increased, right? The red shaded area has increased. So previously, so only this part was red shaded area, this part was red shaded area. Now this red shaded area increased. That means we are maximizing the PD, and that way obviously the low. Now this is the H0 and this is the becoming H1. So it is there now separation between these two are more. So I can detect easily. So the idea of decision theory is to detect two different distributions separately. Okay. So in that case, either one way you can keep one distribution as it is and pulling the other. Okay, that is the case. So that actually we are doing with the NP method. So where we are, that means mathematically what we can say, we are fixing the PA and in this way we are trying to maximize the PD. And that actually we are illustrated here. So nomenclature by fixing PA, okay, by fixing PA, we are somehow maximizing PD. So maximizing PD means obviously, as we have told, if this area is PD, then this red shaded area is the probability of miss, right? This red shaded area in this diagram, lower diagram, this is actually probability of miss. As this green shaded area is PD, probability of detection. So that means there is a relation PM, probability of miss, equal to 1 minus probability of detection, right? So this whole thing is 1. This whole thing is 1. So I can apply that one here. So that is the definition of this one method, nomenclature method is maximizing the PD or minimizing the probability of miss by fixing probability of false alarm to a certain value. That means idea is that I will not allow my probability of false. Means false means more cost, right? As we told. So I will not allow my cost to go beyond certain limit. I will not allow my cost because I am cost sensitive. So I will not allow my cost to go beyond certain limit. I will keep it there. It may be less than that, but it will not cross that limit, cost of that limit. And I will try to maximize my probability of detection. Okay, so that is one of the best things. And in this case, one advantage is that you need not to know the prior distributions of the this happening of H1 and H0. Okay, uh, no prior probability is required for H1 and H0. So you need not to know those things. What are the prior probability of happening of H0 and H1? This P of H0, in which probability they will happen, not required. Not required. P of H0 or H1, not required. Okay. Now see the other method. So this one the method we have understood, right? Now what will be the other method? Other method may be, this is one method, this NP method we told, right? So other method may be, as you told, in this method actually what we have done, we are keeping this one, we are trying to pull this one to the right. Now in other method, what we will do, we will do this one. Both the H0 curve and H1 curve, both will try to means, I will tell both the person to go to change their seat and to sit far apart. Previously, I told only one person to go to more further right side, but now I am telling both the persons to go as far as possible from each other. Okay, so that means I have to pull both the distribution motion in opposite direction. So what will happen? It will. So what will happen? Suppose I have a. So suppose I have now my. Uh, suppose I have my location now. This one 80 location. 80 location is. Now this one is my 80 location. Sorry, H1 card, and this this thing actually came suppose here. Okay. Now what is happening? My threshold is as it is, where it is there. Position. So previously this black shaded area was the PF. Now if you see this, now see this yellow shaded area is becoming PF, right? And now PD is, this one is PD. Now if this part is, now this part is PD is improved. Previously PD was there only this. So now what is happening? Now I can say yes, what is happening? Yes, PF is, so new PF. So this is the dot curve. So PF is decreasing, decreasing. PF is decreasing. Now what is happening with PD? This is the PD part. So this is the new PD part, right? Previously PD was only this part, this small part. Now PD is becoming this much. So PD is increasing. So PD, point of detection, is increasing. Probability of detection is increasing means probability of miss. What will happen? Probability of miss. Probability of miss means 1 minus probability of detection. So that means this one is decreasing. Decreasing. So now I can say, so from these things we can tell that PF plus PM, if we can coin this term as probability of error, both are the errors, right? Both are the errors. If we can coin this term as probability of error, so this probability of error is decreasing. Probability of error is decreasing. So that means in the second case, second scenario, what we are doing, we are trying to minimize probability of error. Okay. and more specifically this definition of probability of error is actually, so probability of error is actually pf into probability of h0 and pm into probability of h1. Okay, that means we can say this pf into probability of h0 and pm into probability of 1, if we multiply this one, so this is the probability of error. So we are trying to minimize probability of error. So we are trying to minimization of Bayesian risk, or we can say minimization of probability of error. Okay, ultimately we are trying to minimize the probability of error. So in the first case, physically what we are geometrically what we are doing, in the Newman Pearson case we are trying to keep the H0 curve as it is, and we're trying to push the H1 curve towards the right. H1 curve towards the right. So H1 curves towards the right. That we have tried to do in the first case, Newman Pearson method. And in effect, what is happening, Newman Pearson method? It is actually fixing the PF, probability of fault theorem is fixed, and by fixing the PF, it is trying to maximize the PD. In the second case, we are trying to push both the curves in the opposite direction, H1 towards the right, so H1 towards the right, H1 towards the right, and H0 towards the left. So in effect, what is happening? Probability of error is decreasing, and obviously probability of detection is increasing. Fine. So, but the issue is that in the second case, what we call this Bayesian decision rule. In the Bayesian decision rule, we to calculate the probability of error, we need the concept of P1 and P0. P1, P0 means probability of happening of H0 means what is the probability that there will be no aircraft? Prior probability. This is the prior probability of H0, right? Prior probability of H0. And this is probability of H1 means prior probability of H1. Okay, probability of H1. So these two prior probabilities should be known to implement this Bayesian uh, decision rule. Okay, so that is one, you can say, constraint to implement the this Bayesian decision rule, because how much time the aircraft will come and aircraft will not come, if you know that one, knowing that one is very tough, right? So to design the general this type of systems, so these Bayesian rules are tough, because knowing the prior probability, is very tough. But in few examples, like for example in few application, like example you can say communication. Okay, communication, where the zeros and ones, these are the two source, right? So probability of 0 and probability of 1. So how many times 1 will come and how many times 0 will come? For example, if it is a random bit stream, so you can say equiprobable. Okay, so that you can assume. So for example, communications, this can be used. Okay, this Bayesian rule, decision rule can be used. Okay, within, but in general, other decision cases, if you don't know the prior probability, so implementing Bayesian decision rules is tough. Okay, uh, so these two, ultimately whatever the decision rules we are applying, suppose it doesn't matter where, it may be in machine learning, it may be in classification problem, it may be in um, uh, spectrum sensing. Okay, ultimately, ultimately, any all the decision rules comes under these two only. Either it will be Bayesian or naming Pearson. Okay. So any nouns, any decision rule you can map it to either of these two uh, decision rules. And there is a performance matrix for a detector. So we call this is receiver operating curve. Okay, so receiver operating curve is a plot between probability of detection along y-axis, probability of detection along y-axis, and probability of false alarm along x-axis. So it is a plot between this PD versus PF. So ROC is a plot where it is actually PD versus PF curve, probability of detection versus probability of false alarm curve. And if we see, if the 45 degree line is actually 50% probability, is a 50% line. Okay, means if you do nothing, if you do a tossing a coin and take for any event, any binary event, if you simply tossing a coin and take the decision, that means actually this 45-degree line. So any decision would be better if it is inclined towards this upside. Means for small PF value, you have to get more PD. For small PF value, you have to get more PD. For small PF value, you have to get more probability of correct detection. Okay. So as much as the curve will be bent towards the leftmost corner, so more better detector you have designed. There are other few performance metrics are used, especially in communication, for this PD versus SNR versus PD. Okay, how the probability of detection is changing with the varying SNR. Okay, but the most important thing, whether a detector, if you got a detector, if you got a detector like if you got a detector like this way, this is wrong. That means something is wrong there. It may not happen, right? It may not happen below 45-degree line, because if you doing nothing, simply tossing a coin and taking the decisions, obviously for a binary event we are talking about always, binary hypothesis testing problem. So that is enough, right? Enough for this 45-degree line. But anything you are getting below this one, so that means always the ROC curve should be always concave. Okay, those are the concave curve. So concave. So if it is concave, then it is okay, but it may not be a convex curve. Okay, may not be a convex curve. So this type of curve is not allowed. It means something wrong there in your calculation. Something wrong in your calculation. Okay. Uh, so this is the uh, things, and now see if how you will apply this one in your distributed. detection scenario in case of IoT. Suppose you have uh, different sensors, suppose temperature sensors in a industry workshop. Okay, you have different temperature sensors in different corners. Okay, so sensor 1, sensor 2, sensor 3. Okay, different sensors you put. You got different sense data. Now you need from all the thermometers, all the sensors you got different. So you now have to take a decision fusion. You need a data fusion or decision fusion. Okay, so you have to this each of the decision you are taking, each of the decision you are taking either with NP or Bayesian. Okay, either NP or Bayesian. This each of the individual detector are working, and then you have to fuse all those things in a common center or in a distributive way. Fine. So ultimately, you have to do a data center to get the final temperature. Okay, so temperature is the parameter. Temperature is the sense data. So that means ultimately you have to fuse those things. So that is well studied problem in sensor network, wireless sensor network. If the channels, if those channels are wireless, if those channels are wireless, those channels are wireless, all those channels are wireless. So you can say this is a example of WSN, problem in WSN, and parallel can be used for IoT system. Okay, so application to IoT you can say. So this way you can see this the decision problems, how it is important for the IoT, and theoretically ultimately you are using this type of decision problem. You have to solve this type of decision problems to implement your IoT network. Okay. Now the last part is I want to conclude with this estimation theory. So this is another inference problem. Okay. So that in decision problem you are taking the decision about the source, means what was there. It was something or nothing. For example, a binary case. Okay. Now same way for estimation theory, basically you are trying to estimate some parameter. So some parameter of the signal is missing, suppose the amplitude or the suppose the sign or suppose the phase. Okay, some parameter is missing. You have to estimate that parameter, and ultimately any real time problem will be combination of these two. Means how, first you have to estimate the parameter and then you have to apply it on the decision. Okay, so basically any real time IoT problems, inference problems actually is a combination of this any real time of your this estimation and detection problem. Okay, so in the estimation theory, same the different components of estimation theory. If we see the different components of estimation theory, uh, the first is that parameter space, means what are the parameters. So you are seeing in this parameter space, it may be amplitude, it may be phase, whatever. Okay. So that way the parameters are coming. and then again the observation space. Okay, so first is the parameter space, then the observation space means where you are observing. Okay, now again there will be a probabilistic mapping. There will be a probabilistic mapping from this parameter space to observation space. From parameter space to this observation space. Observation space. There will be a probabilistic mapping because it is you are seeing the things over a noise environment. Okay, that is the same thing like previous. And then you are applying some estimation rule. Applying some estimation rule. Okay. For example, so in any estimator you can say for suppose for this example, suppose you want to estimate the DC level A. DC level A. So this is the parameter of interest. So this is the parameter of interest, theta, parameter of interest. You have observed, this is the observed signal, observation. Okay. So this is the noise. Over a noisy channel, you have sent some DC value and you have observed X at your observation space. So now you want to estimate this DC level. Okay. So estimate would be done through some estimator, right? So estimator is the estimate of the parameter of the interest. It is actually some kind of formula. So what you can do, suppose this is the same nth sample equation. So I can say my estimator, suppose I can design different type of estimator. For example, I can take one estimator where it will take all the 0 to n minus all the samples, it will take sum and take the average. That may be one estimator. I can take only suppose the 0th sample, that may be my estimator. I can take some more complex things. Okay. Okay. So like the first two times of the first sample, then sum of the all n minus two samples into 1 to n minus two samples, then the two times of the last sample, and by dividing by all n plus two. Or I can take all the n minus sum of the all the samples in samples divided by 2n. That also I can take. So this different way I can estimate the things. Fine. So my estimator may be different. So that's why this formula may be this one, maybe this one, maybe this one, whatever. So if my formulas are changing, so it may the estimated value will be changed. Fine. And but which formula should I take? Where the error of estimation is minimum, right? Obviously, I'll try to minimize the error of the estimator. That will be my ultimate goal. So where the error of that estimator will be minimum, okay. So error will be minimum. That is the ultimate aim to choose. Now these estimators can be classified as uh, mainly two categories. One is Bayesian estimator and is classical estimator. So if the parameter of interest is random, so I have to apply. If the parameter of interest is random, so I have to apply this Bayesian technique. And if the parameter of interest is deterministic, but may unknown, that is fine obviously, but it is deterministic. So I don't know that one, but it is deterministic. It will not change. Right? That is 2 volt to 2 volt. It will not like in this example. Like in this example, suppose this is the DC value. Okay. So in this case, DC value will be what? So either this is this one, or this is this one, or this is this one, something, right? All are DC values. All are DC values, right? So I can say A is here DC value, DC level is a deterministic. Deterministic parameter. Deterministic parameter. Deterministic parameter. But if suppose I have x n equal to um, sine theta plus wn, if I want to tell theta is my parameter, phase. So phase is changing. Phase is changing from 0 to 2 pi, it is changing, right? Phase is changing. Phase is changing from 0 to 2 pi. So phase should be characterized as a random variable, random parameter. It is a random parameter. It is a random parameter. Correct. So based on this type of nature of the parameter of interest, we can classify the different estimation algorithms, either Bayesian or classical. So under this classical estimation, you have already known the methods like maximum likelihood method, minimum variance unbiased, method of moments, best linear method. Also, the most important of among these are actually this maximum likelihood estimation method or this least square method. If you see in any and one more thing, exactly in which problem, what type of estimation algorithm will be used, that may not be properly defined like the decision problem. Okay, but somehow it is categorized like this way. So at least if the parameter of interest is deterministic, so you can go either of these maximum likelihood or least square. Okay, whatever is applicable. But which one will be more efficient in which scenario, that actually depends on the application to application. And same way, in if the parameter of interest is your random, so in that case you can go for in that case you can go for your this uh, Bayesian techniques, which are common Bayesian techniques are minimum mean square, MMSE, so which is commonly used in communication systems, and this map estimator, that is also commonly used in communication systems. So maximum a posteriori estimation technique, and some linear version of this minimum mean square. So that different methods are used. So mainly in terms of classical, either MLE or LSE are used, or in terms of Bayesian, generally MMSE or MAP is used, right? So these are the few things about the classifications of the different estimator, and some properties of good estimator, you can say. So estimator should be unbiased, obviously. If you are estimating about anything, and if you are biased to some values, so obviously it is not fair, right? So that way, a good estimator should be unbiased, and means bias of that is expected value of the estimated, the difference between the expected value of the estimated value, expected value of the estimator, and the original value is zero. So that is called the this, that means bias is zero. So definition of the bias is the difference between expected value of the estimator and the actual value. That is the definition of the bias. So bias should be zero in case of unbiased. So any estimator, if bias is zero, that is better. And second thing, estimator, one estimator would be called efficient if its variance is less than the other. Variance means, suppose I am estimating about the temperature. Okay, so I have a thermometer. I am estimating with that one. So today I am measured the temperature something, tomorrow some different values. Okay, suppose today 20 degree, tomorrow 18 degree, day after tomorrow suddenly 10 degree. Okay, but actually this much is not the case. And suppose if I am checking with another thermometer, which is actually today 20 degree, tomorrow 21 degree, day after tomorrow 18 degree. Okay, that way. So I can say the variance of the second thermometer is less than the variance of the, in the same environment I am talking about. In the same environment I am taking the measurement with the two thermometers. So I can say that variance of the second thermometer is less. So that way I can say one estimator is efficient if its variance is less than the other. Okay, and consistent property means actually uh, if it is goes for error is negligible. Always that error, if we go for number of trials, number of measurements, always the error will be very negligible. Okay, so that error tends to zero always. So that way we call it is a consistent estimator. And sufficient statistic, so four major properties of a good estimator. One is unbiased, one is efficient, one is consistent, and another is sufficient. So this sufficient is not a property, it is a statistic. Means if you go to the first example here, if you see sufficient statistic means, see the first estimator, this first estimator I have taken all the samples from 0 to 1. But in the second estimator, I have only taken this one sample. So this, what is the measurement I am taking? That is called the statistic. Means all the samples. This is one type of measurement I have taken. Only the first sample. That is one type of measurement. So here the statistic is, I can say the, so I can say the here the statistic statistic is x0 to x n minus 1, all the samples, right? So this is my statistic. Here statistic is only the first sample. Here statistic is x0 to xn minus 1 and another x0 and another xn minus 1. So this is a, you can say the exact whatever is what the all the samples is actually all the samples. This is underestimated measurement, and this is, you can say, overestimated, right? So that means this is the only case where sufficient, what is the sufficient part, mane minimum how much is required. This sufficient condition to take the measurement that is present in the first one. In the second one, not all the samples present, so it is not sufficient. In the third one, it is more than sufficient, right? So we have all the 0 to n minus 1 samples. Moreover, I have taken extra another sample, first sample, and another last sample. So this is the third one is more than sufficient. So more than sufficient. This is under sufficient. Under sufficient. And you can say this one is a sufficient. So the statistics should be estimator should be designed such a way the statistics should be sufficient. Okay. So that is called the sufficient statistics. Okay. So these are the estimation accuracy and some performance metrics like their performance metrics was the ROC curve. Here performance metrics will be some lower bound Kramer Rao lower bound we use for the performance metrics. Uh, so that's it. And so some one of these inferential statistics actually are used in either in the statistical inference like this estimation or in somehow some the forecasting things like the part of the statistic that allows researchers to generalize the findings beyond the data collected. So you have collected up to suppose n samples. So if I go for another 100 years, so what will be the forecast about the that parameter? So that type of forecasting or beyond the data collected, that is actually called the inferential statistics. So that also used in actually from a small domain, your small sample domain, you are forecasting about a larger sample domain. So that is actually the inferential statistics, and statistical inference is from you have collected whatever the data you have collected, from there you are inferencing about the problem, about the parameter. So everything actually are used in the IoT things. So I think that's enough for my talk. Any question from?
Participants, if you are having any queries, kindly post it in the chat box. Kindly post it in the chat box if you are having any queries. Thank you, sir.
Okay, okay. Okay.
Really, it was a valuable session for all of us. Actually, your most valuable talk on IoT will be very useful for every participant. It was really an eye-opening session for the pillars of IoT. We got a lot of information on IoT from you. Actually, we are sure all the participants would have attained a good knowledge on what is IoT, its design, decision theory, estimation theory, and others. Once again, we thank you for your valuable inputs given, which will certainly improve our ideas on IoT. We are eagerly looking forward for more such interactions in the years to come. So, thank you once again for spending your precious time with us. Participants, thank you for your cooperation today. Let's meet in tomorrow's session by 10 a.m.
Okay, thank you all for your patience and your cooperation. Thank you all. Yeah.
Thank you, sir.
Mm,
Thank
yeah.
you all.
Mm.